Hello everyone. In this video, I'm going to solve an example of analytic forward kinematics using the Denavit-Hartenberg or DH convention. And we are going to use a PUMA 260 robot with 6 degrees of freedom. All joints are revolute joints, so theta 1 to theta 6. At the end of the 6th joint, I have added a gripper. And as I said, we are going to set up the DH axes, fill the DH table, find the A matrices, the T of 6 with respect to 0, and find the rotation matrix and position of the end effector with respect to base. Dimensions of the robot are given, the ones that we need. And if you start, the first step in DH is to find the Z axes, which are the actuation axes. Now Z0 is already given to us for theta 1, so let's focus on Z2 all the way to Z6, Z1 to Z6. Z1 is the actuation axis for theta 2. So here this is going to be Z1, right? Let's write it down here. Then we go to Z2, that's for theta 3, right? Let's just put it here. Maybe a little bit longer, or we can make it short, doesn't matter. So Z3, Z2. Z3 is for theta 4, so it is going to be like this. Z4 is for theta 5, so it will be like this. Z5 is for theta 6, so it is going to be upward. And Z6, which is for end effector. For end effector, DH convention does not have a specific thing. But one of the suggestions we have in the literature is this system of NSA or ASN or SAN, doesn't matter. So if we say ASN, the ASN approach for setting up the end effector axis, as you know, A is approach, S is slip, and N is normal. And as long as the setting up of these axes is not going to violate the two important DH axioms that we're going to talk about in a minute, then we should be fine using that. So A, as I said, is called the approach direction, and that's the direction that your gripper is going to approach the object to grab it. So that we call it the Z of the end effector. S is the slip direction. That's the direction of closing or opening. We typically use that for Y of the end effector. And then we have N, which is normal. That's perpendicular to the two previous directions. And we use this to be X of the end effector. So for now, let's go with this, and hopefully we'll see it doesn't violate our DH axioms. So Z's approach, if that's the case, approach of these gripper toward the object is going to be the same as Z5. So I can say Z5 is also the same as what? Z6. They are on the same line at the moment. Okay, so these are our Z's. Now it is time to set up the origins and the x-axes. Now, for X of the base, there is no mandatory thing to observe, because the two important DH axioms are each X should be intersecting the previous Z and should be perpendicular to previous Z. And since there is no previous Z, right, there is no Z minus 1 for X0, therefore, X0 can be selected arbitrarily, as well as origin 0 can be any point on Z0. So here we chose it to be at the bottom of the joint, and X0 and Y0 we selected this way. As long as they form a right-handed system, we are okay. So frame 0 is already given to us. That's not a big problem, but we could select it anywhere conveniently. Now it is time to go look at x1. x1 has to be perpendicular to z0 and intersecting it. Now, when we determine the x's, we always look at the situation between previous z and the current z. So z0 and z1, if you look at them, they are perpendicular to each other and intersecting already at this point. So the intersection point is going to be origin of frame 1. And x1 has to be perpendicular to z0, and naturally it has to be perpendicular to z1. So the only solution for it is something like x0, right, which is perpendicular to the direction of z0 and z1. So I am going to select a direction similar to x0 for x1. Another thing we have to consider about DH is we'll try to select frames from one to the next that need minimal rotations and minimal translations. So we make many of those DH parameters to be 0. That's the best selection if you can do. So here, this is going to be my x of 1. If you remember from DH, we use 4 parameters to go from each frame to the next frame, right? Or describe the position orientation of one frame with respect to the previous one. And we call them theta, dA, and alpha. The length, the angle of the basically the joint. Then we have D, which is called offset. Then we have A, which is the length of the link. And then we have alpha, which is the twist angle. And we need only 4 parameters, not 6. You know, in general, we need 6 parameters to describe one frame with respect to another, 3 for position, 3 for orientation. But since we have 2 axioms, actually out of 6 parameters, 2 of them will be redundant, so we only go with 4 parameters. And out of these 4 parameters that you use for each frame to the next, if you can make as many as possible 0, that's the best selection of your axis. So if you have a room to select something, try to align your x with the previous x, your z with previous z. Of course, z's are out of your control, but x's, if you can align with previous x's, that makes your solution a little bit simpler. So here, that's your x1, that's your z1, and y1 has to be such that the system is a right-handed system. Therefore, y1, the only choice for it is downward, like this. Okay, so y1 is automatically determined. Many people, when they do DH, they do not even show the y-axis because they do not have much of importance. All you need really is x and z, because that's how the DH is defined. The y's will automatically be aligned with when you align x's and z's. But here, for more clarification, I show you the y-axis as well. So that's frame 1, that's origin 1. Now we go to frame 2. If you look now, z1 and z2 are parallel. That means the origin of frame 2 can be selected anywhere arbitrarily along z2. And x2 has to be perpendicular to z1 as well as z2. So now you might say, well, can I select it to be something like y1? No, because if you do so, then this x2, I'm sorry, is not going to intersect z1. It's going to be askew with z1. Okay, so the only solution you have for x2 is something similar to what? x1, which when you extend it, it is going to intersect the extension of z1 at this point. Okay, so what we do here is we select, as I said, x2 to be similar to x1. But where would you put the origin? As I said here, I put the origin in the middle of thickness of this member number 2. So I put it, or 3 you might call it, I put it here in the center. And that's where this Z3, extension of Z3 is going to pass. Okay, so if you extend this Z3, it is going to pass from the middle thickness of the member. Right, and since the middle thickness of this trapezoidal member is right above the cylindrical member, then this distance 3 inches is going to be the distance between origin 1 and origin 2. Okay, so here we go. I select my x2 to start here from the middle thickness, and then of course when you extend it, it is going to align with what? It is going to align with, let me just continue it until here. It is going to align with x3. So here, this guy is going to be your x number 2. Let's see if I can put it somewhere next to it, or maybe make it shorter. It's typically not a trivial job to squeeze all of those many x's here in a very limited space. So maybe this is good enough now. Good. So that is my x2. And if that is my x2, then your y2, considering that z2, that's x2, your y2 has to be downwards, so z2 is in that direction shown. So y2 is going to be similar to y1, but downward in a separate location. So here we go. This is going to be your y2. What's next? The next one is, of course, x number 3. So what's the situation here? If you look, z2 and z3, if you continue z3 and z2, they already intersect at this point, at the origin of 2. Therefore, this origin of 2 should also be origin of 3. There we go. And if that's the case, then x3 has to be perpendicular to z2 and z3, so it has to have something, be aligned with y2, either upward or downward, but the same line. So I select it to be the same as y2, so I call it x number 3, right? And so for that reason, I have to extend my z3 all the way to be what? Go to the origin of 2. So origin of 2 and origin of 3 are going to be on the top of each other, and for that reason I can get rid of this line for x2 and make both of them to be the same thing, right? And that makes this whole thing a little bit easier. So let's go, here we go. Like this. And as I said, for that reason, now I can say x2 is on the top of z3. Good. So frame 2 and 3 have the same origin. Now I need to go to z4. z4 and z3 also intersect, but at this wrist center. So that's going to be origin of 4, and x4 is perpendicular to both z4 and z3. Therefore, it can be something similar to y2 and x3, but in the separate location. So let's do that. And here, I'll go down like this and call this guy x number 4. And as you can see, it has a similar direction as x3 and y2. So between x3 and x4, there is not a ton of rotation that you need to do other than, of course, theta 4. And if that's x4 and that's z4, then y has to be something like x2 and z3. Whether forward or backward, we have to check for a right-handed system. And you'll see that if you'd want to be right-handed, then y4 has to be backwards compared to x2 and z3. Okay, so we have to pay attention to that part. And for that reason here, I'm going to use a little bit thicker marker. Let's see, and show that y4 is really backwards like this. Maybe too thick, but that should be okay. So the thick one over there is going to be y number 4. And now we go to 5. x5 is perpendicular to z4 and z5. z4 and 5 already themselves are perpendicular at the rest point. So x5 has to be something like x2 and z3, and therefore I select it to be the same as them. Okay, so this is also going to be my x number 5, right? Perpendicular to z5 and z4. And if this is x5 like this and z5 is upward, then your y5 is going to be the same as z4. Finally, we get to z6 and z5. They are on the same line here, parallel or collinear, and therefore the origin of 6 can be selected anywhere along z6. And we select it to be not at the rest point, we select it to be here at the center of the gripper and use this 3-inch distance for it. So that's where we put origin of 6, and x6 has to be perpendicular to both, so it is up to you. You can choose it to be any direction. I choose it to be something parallel to x5, therefore I choose my x6 to be like this. And if that's x6, then that's z6, then this is also going to be y6. There we go. So now finally my x's are set, and it is time to go ahead and fill the DH table. Okay, so let's go ahead and fill the DH table. For that, maybe I create a table right here. So insert a table, and I need a 5x7 like this, right? And then this table I can resize. Okay, so this is going to be my table, and I can resize anything in it. So it has 7 rows, 6 of them are for the 6 joints, correct? So the 6 variables, so this is going to be I of 1, right? Or I can just say 1, 2, 3, 4, 5, and 6. Right, and let's use a bigger font here so we can all see it. There we go. And what we have here is going to be the first variable is theta. So this is theta under sub I. Then we have D. Then we have A, and then we have alpha. Okay. So the meaning of these guys are clear, but I'm going to explain them for you one more time if you forgot. So theta is the rotation about your zi minus 1 to align xi minus 1 with xi. Di is the displacement allowing zi minus 1 to go from origin of I minus 1 to origin I. Ai is the displacement allowing nu x xi to go from origin I minus 1 to origin I. And alpha I is the rotation about x nu or xi to align zi minus 1 with zi. Okay, so if I want to just kind of summarize it, these two are about or along zi minus 1. these two are along or about what? Xi. Okay, and then the first one and the last one are rotations. The two middle ones are the displacements to set the origins. Okay, so theta I is to align xi minus 1 with xi. Alpha I is to align zi minus 1 with zi, and di and ai are to align oi minus 1 with oi, the origins. Okay, so these are the four parameters of DH. Please watch my previous videos on DH convention if you want to get a clarified definition of these, right? Look at the shape of the DH that I provided, so you can review that. So here, if we go, the first thing is how much rotation do I need about z naught to align x naught with x1? Well, the way it is shown, you will say, well, they are already aligned, no rotation. But yes, that's when joint 1 has not rotated yet. When it starts to rotate, then this trapezoidal member will face the other way, and x1 will be rotated with respect to x0. Therefore, this angle is not just going to be 0, it is going to be actually what? Theta 1, right? The joint variable. Then when you want to go from origin 0 to origin 1, do you need to move along z0? If yes, how much? You see that is 13 inches to go from here to here. So that is your d. Do you need to move along the new x now to go from this origin to this origin? No, they are only, all you need to align them is to move along z0. No displacement along x1 is needed. They are right on the top of each other. So x1 is no motion along x1, so a0. And now, do you need to rotate about x1 to align z0 with z1? The answer is yes. If you look here, this is your x1, this is your z0, this is your z1. They are not aligned, even if there is no rotation theta 1. You definitely need to rotate this 90 degrees clockwise to align, but the positive rotation about x1, if you use the right hand rule, it is counterclockwise. Okay, so since the positive rotation about x1 is counterclockwise and you need 90 degrees clockwise, therefore your twist angle is going to be negative 90 degrees. Okay, so this is how you get row number 1. Now you go from 1 to 2. When you go from 1 to 2, first thing, do you need to align the x's? This is x1, this is x2. Again, the way they are shown, you might say, well, I don't, but you do when this theta 2 starts to rotate. Then this member, the third member with respect to the second member, the direction of x1 and x2 will be different by amount theta 2. So yes, you need theta 2. Do I need to move along z1 to go from this origin to this origin? The answer is yes. You need to go backwards by an amount of 3 inches first, and then move along the new x this much to align. So yes, you need to go backwards by 3 inches. So it is going to be negative 3. And then once you go from here to here, from here to this new origin, you also need to go what? 8 inches along the new x, x2 to align, so this is going to be 8. And when you get there, now compare your z's. This is what? This is z1, right? This is z2. Well, they are already parallel. You don't need to align them. Therefore, no twist angle is needed. So it is 0. Good. Then what? Then we go to between 2 and 3. What do we need between 2 and 3? First, we look at the x's. Do you need to align the x's? x2 and x3. Well, where are they? The x2 is here, and x number 3 is here. So x3 is down, x2 is this way. And although I need my angle rotation theta 3, but even when theta 3 is 0, they are not aligned. So even when theta 3 is 0, your x2 is like this, your x3 is like that. And this is your z number 2, for which a positive rotation means something like this. So before I do anything, before even this rotation theta 3 happens, I first need to align x2 and x3. How much is the rotation? That's a 90 degrees. And this direction of 90 degrees matches the direction of theta, right? So before I do any theta, I need the 90 degrees to align, then I can apply theta 3. So the total angle is going to be theta 3 plus 90 degrees. Now what? Now that I got my my x's aligned, now I want to go from origin 2 to origin 3. But the thing is, origin 2 and 3, they are both on the top of each other. So no motion along z2, no motion along x3 is needed. So both of these distances are 0. And then do you need to align the z's? Well, that's z2, this is z3. Let's find it. It's just too crowded here. And clearly z2 and z3 are not aligned, so you need to align them. So definitely you need a twist angle. Let me draw that shape for you here so we can figure it out. So if you look here, your z2 looks like this, your z3 looks like that. And then the new x3 is like this. So what kind of rotation do you need to align z2 to z3? This much, 90 degrees. But positive rotation for x is going to be what? If you use your right-hand rule, it is going to be like this, which matches that direction. Therefore, you need a positive 90-degree twist to align what? z2 and 3. There we go. Now we go from z3 to z4, right? Or frame 3 to frame 4. What do we need? Well, first we need to align the x's. Where are the x's? We need x3, which is here, and then we need x4. The good thing is this time they are already aligned, so all I need is when this theta 4 is happening, I just need to apply theta 4, nothing else. And that's theta 4, that's good. Now what? Now, how do you go from origin 3 to origin 4? Origin 3 is here, origin 4 is here. Do I need to move along old z or z3? Of course, you need to go by this distance, which is what? 8 inches to go from origin 3 to 4. So that distance is 8 inches. Do you need to move along new x4, which is downward? No, they are horizontally aligned, so no A is needed. And what about the z's? Are they aligned or not? Well, if you look, they are not. This is z3, this is z4. They are not aligned, and therefore you need to align them. So here again, I draw the shape for you. This is z4, this is z3, and x4 is downward like this, correct? And the rotation that you need is this much, 90 degrees. And again, if you remember, I told you that the positive rotation for this guy is like this, because that's similar to x3. So So it's similar to the previous case. And this one and that one are clearly opposite of each other. So you need a negative 90 degrees twist to make it happen. Fine. Now let's go to the next one. The next one is going to be going from 4 to 5. And now if you look, your x number 4 is here, your x number 5 is here, right? And then rotation number 5 is going to be this guy here. So this is x4, this is x5, this is z4. And clearly, before even rotation theta 5 is happening, you need a 90-degree rotation, and that is opposite of the rotation positive for z4. So you need a negative 90 degrees before theta 5 can happen. So it is going to be what? Theta 5, and then minus 90 degrees. Good? Now, finally, we look at the origins. Origin of 4 is here, right? And if you look at origin of 5, that's also there. So 4 and 5 have origin on the top of each other, so no displacement is needed. And what about the z's? So now you look at z4 and z5. That z4, z5 is upward, so they need to be aligned. This is z4, this is z5. And you need new x, x5, which is like this. And you need this rotation to happen, and the positive direction for x5 is the same, right? So definitely you need positive 90 degrees. Finally, you go from 5 to 6. Z5 and Z6 are aligned. What about the x's? X5 and X6 are also aligned. So the only angle you need is really theta 6. The origins of 5 and 6 are not the same. Origin of 5 is here at the wrist center. Origin of 6 is at the gripper center. You definitely need to move along the old Z. How much? So what you need here is 2 inches plus 3 inches, right? Because by 2 inches you go from center of this wrist to the center of the end effector, and then another 3 inches to the center of the grip, so it is going to be 5 inches. And then you don't need any motion along new x. And now what about the z's? The z's are already aligned, so no twist is needed. There we go. So finally, I guess I got my DH table complete. And now I'm ready to apply them to the general homogeneous transformation matrix of DH, which, if you remember, it is of this form. So you take the values of each row, the thetas, d's, a's, and alphas of each row, you apply it, it gives you one A matrix. Each A matrix will take you from one frame to the next. So if you apply row 1, these 4 numbers, it will take you from what? Frame 0 to frame 1. If you apply second row, right, then it gives you A2. A2 is the one that takes you from frame 1 to 2 or back from 2 to 1. This one is going to give you A3. This one is going to give you A4. This one is going to give you A5. And this one is going to give you A6. And if you multiply all of these A's together, T of 6 with respect to 0 is simply the product of all of this pre-multiplication. This is going to give you what? The end effector in base, or the gripper in base here. And this is going to be a 4x4 matrix, which has a rotation matrix in it, R of 6 with respect to 0, the origin of 6 with respect to 0, 3 zeros, and a 1. And the goal of in forward kinematics is to find these guys. If I give you the 6 values of what? Theta 1, 2, 3, 4, and 5. In many DH tables, you probably see a star next to the thetas to tell you that these are the joint variables. And the rest of the parameters in each row are just constants. Okay, so if we plug these and form the DH table and write a Matlab code, we can get our R of 6 in 0 and D of 6 in 0. And here I wrote a Matlab code to do that, so let me show you. Okay, so the code I wrote is using a function, and this function, once you pass it theta, D, A, and alpha for each row, it gives you back the corresponding A matrix. And as I said, it is doing it using this general DH homogeneous transformation matrix. So these formulas are exactly reflected here. You can see this is a 4x4 matrix I have. And now in my script, I have my DH table just the same way that we did it, right? We found it, except that the degrees are converted into radians here because I'm using the functions sine and cosine, not sine D and cosine D. If you use sine D and cosine D, then you're good. Just directly use 90 degrees instead of pi over 2. So here, as you can see, I chose some values for theta 1 to theta 6, 30 degrees theta 1, 15 theta 2, 20 theta 3, 45 theta 4, 60 theta 5, 120 theta 6. Feel free to, when you use this code, feel free to modify the values of theta 1 to 6. The DH table is going to be the same. You're not going to change that. This function is going to be the same. So first I call that DHA function with values of what? Row number 1, right? So I said row number 1 and 1. So that's your theta 1, right? Or theta in the first row. This is D in the first row. This is A in the first row. And this is alpha in the first row. So first I set T to be A1, and then from 2 to 6, I kept getting A from the new row and multiplied the T, which was A1, by the new A. So now it's going to be A1 times A2. When I becomes 3, going to be A1 times A2 that it was already times A3, and then keep what? Going forward and multiplying all the way to A6. So at the end of the day, T is going to be all of those A's multiplied together from A1 to A6. And then the last column of that, elements 1 to 3, are going to be end effector position. And then the 3 by 3 minor of it is going to be what? The rotation matrix, right? So that's all I need to simulate this. And here we go. As you can see, it says the end effector position with respect to base in inches is 18 along x0, 5.29 along y0, and 5.3 about z0. And these are the rotation matrix, right? The first column describes x of 6 with respect to x0, y0, z0. The second column describes y of 6 written in frame 0. And the third column describes what? Z of 6 in the 3 axes of frame 0, correct? So 18, 5, and 5, right? So 18 about x. So you have to add 18. So it's already an 8 and 8. And because of the angles, this 5 inches is tilted to the right. So, and then 5y and 5z, right? So your end effector, the center of the rest really is going to be somewhere like 5-1 and 5z. Well, let me make sure. Yes, because these guys are going down. So it is going to be somewhere down here with those angles. Okay, this is where the end effector is going to be, and then the x of the end effector, x of 6, is going to be what? It's going to be mostly along z of the base, mostly. So the x6 is going to be mostly aligned z. The z of that, let's look at z of that. Z of that is mostly aligned x of 0, right? So this is x of 0. Z is going to be mostly aligned that. So it is going to look something like this, because that's the z6 is going to be kind of similar to x0. X of that, which is normal to it, is going to be mostly aligned with z0, right? As we said. And then y of that is going to be opposite to y of the base. So if this is y of the base, it is this way. So it is going to open and close this way. But that's okay. So it's going to be like, this is going to be your y of 6 almost. This is going to be your x of 6. And this is going to be your z of 6. And the rest of the robot is formed such that your end effector comes here with those 6 angles. Okay, again, if you neglect these other small numbers and consider this to be 1, this to be -1, and this to be 1. Right? So this is where the end effector is going to be, right? 5 inches above the origin, 5 inches to the backside, and then about 14-15 inches on the x direction. So this is going to be your end effector position and orientation. Hopefully this example was useful to you, so I will see you in my next video. Thank you.